Welcome back. This is lesson 2.4. In this lesson, we are going to be taking what we learned about looking at amplifiers in a feedback topology from last video, and we're going to be applying that to actual op-amp networks. So just a quick refresher from what we did last time. Last time we looked at amplifiers modeled as feedback networks. And so that's, an example of that is shown on the left here. These are sort of all the parameters we looked at. But the basic idea here is we have some forward gain, which is that A epsilon, and then we have this feedback factor, this feedback gain, which is B or beta, depending on the textbook. There's slight differences in the way these terms are referred to. This textbook uses B. Beta is commonly what you'll see in control systems. It's usually an alpha beta in reference to forward gain and feedback gain. So just be aware of that difference. But looking at this system, the whole reason we developed equations for this system is because once we're able to develop equations for the generic case of a feedback network, all we need to do is identify the parameters of this network for whatever particular op-amp circuit we're dealing with, and we'll be able to recycle all of those equations. How do we get the parameters though? The problem is when we build a circuit with op-amps, right? It's an op-amp and a bunch of resistors. It's not a nice clean A epsilon and B that's easily apparent. So we need to take our system of op-amps and resistors, and we need to convert them into a form where we can identify these values. And the best way to do it is if you look at this output here, what is this? This XO is the input times A epsilon, and then this XO gets amplified by B and subtracted from that. So basically we have, so the signal here, the signal right here, this error term, that's X input minus B X output, and then that whole thing gets multiplied by this A epsilon. And so that's the expression that we have here. And this is really handy because if we, this equation relates input and output. And if we are able to analyze any op-amp circuit and find a relationship between the input and the output, and we're able to massage the equation into this form, then we're able to identify these critical parameters here. This A epsilon and B is what we really want. And once we find that A epsilon and B, then we're able to use all those, we're able to find the loop gain, we're able to use all those equations we dealt with last time. Okay, so what's the process we're gonna go through? Anytime if we wanna analyze an op-amp, we wanna analyze it using this model, this feedback model. First of all, what does it mean to do this? Well, it means that we are assuming non-ideal gain. We're assuming an op-amp that has a non-ideal alpha. Now we could have an op-amp that still uses an ideal alpha, an infinite alpha, and we still might have a finite open loop gain for our overall circuit. But for this analysis, generally, the limiting factor that we're dealing with is finite open loop gain for the op-amp itself. So in order to analyze any op-amp configuration, again, assuming non-ideal open loop gain for the amplifier itself, we basically need to find the equation that relates the output and input of that amplifier. And then, as I mentioned previously, we need to manipulate algebraically that expression until it's in this form. Once we have that expression in this form, we know whatever term is here and whatever term is here, that's going to be our A epsilon and our B. So you'll notice this expression has XO equals A epsilon times XI minus BXO. So why X's, right? We don't, in circuits, we deal with currents and voltage. Why not say VO or V out or IO or I out, IN, I out? The reason we don't do that is because the input and output can be any form. So we're talking about analyzing now circuits that we build with op-amps. We can build circuits for op-amps that compare currents at the input and output of voltage. We can build circuits with op-amps that compare voltage at the input and output current. We can do voltage in, voltage out. We can do current in, current out. So even though the op-amp itself is a voltage amplifier, We can use it to build all sorts of circuits that amplify currents and voltages, input and output currents and voltages. And so we leave it as XO because we don't know. The input could be, it could be a current input, it could be a voltage output, whatever. And it's going to vary. It's going to vary depending on our particular topology that we're dealing with. But that's really the key thing before we get started in this is what we are talking about now is analyzing circuits that we've built using an op-amp at their core. We are not analyzing the op-amp itself. And the really important thing about that is if we're just looking at an op-amp, the op-amp itself, the open loop gain is alpha. There's A. But when we're talking about the open loop gain of a system, it's this A epsilon. So they're two different things. So keep that in mind that we're just trying to find these parameters for complex systems, not for an amplifier itself. So let's do one of these problems. So let's analyze this circuit here. You might recognize, well, you might not recognize this particular circuit. We have a current input, IN, and we have a voltage output, VO. So this looks like it's current in, voltage out. So what we're going to do to analyze this is we are first going to write an expression that relates the input to the output. How are we going to do that? Well, the best way to do that is that I've found is to model the amplifier as with a substitute circuit, with an equivalent circuit. The thing to point out though is we cannot simply assume that Vn is equal to 0. If we're normally doing an ideal assumption analysis, then we can just say Vn is equal to 0. That's not what we're doing. So we still have to represent Vn as a variable. We still have to deal with it as a variable. So let's build our equivalent circuit here. So if we're looking at this, we have some current supply, IN. We have some resistor R. We have oops, I don't know what happened here. So this is our equivalent circuit. Now let's stop and think about this. So why did I draw VO as a voltage supply? Well, ultimately that's what this amplifier is doing. Ultimately this op amp has as an output, it's outputting a voltage. So it's outputting a particular voltage. We don't necessarily know what that is at this time, but we know the voltage at this node, which is this node on the circuit, is VO. So we can model the output of this op amp as just a voltage supply, VO. The load is in parallel to that. So this RL here is in parallel to that. And then we have this resistor R, this feedback resistor R. Now the thing is, this node right here of our circuit, this is Vn. And that's important to remember. And that is not 0. So we have to be careful. We can't just say that's 0. But the question is now, let's see if we can write an expression for Vn as a function of V out and I in. Well, there's several ways we can do it. We basically have a circuit here, right? We have, if we're trying to find the voltage of this node, we can choose any circuit analysis technique we want to find this. The book tends to like to use superposition. And the book tends to like to use superposition because it gives you your answer in a very clean format. It's also a fairly quick way to do it. So a lot of these types of op-amp circuits are going to have the output voltage and they're going to have some input current or voltage. So usually there's going to be, when you're doing this analysis, there's going to be two supplies. Sometimes superposition is a really fast way to do two supplies. So what's superposition? So if you want to, you can go back and watch. If you look at my lecture series, if you look at my YouTube channel, there's a EE 111 lecture series. That lecture series, around the end of chapter 4 in that lecture series, I discussed superposition, but we can really quickly just go over superposition from scratch right now. It's one of the things the book doesn't really do. It kind of just assumes you know it. And you should know it as it's a prerequisite to if you're taking this class, but if you don't want this refresher, just fast forward. So I'm going to go through and do it. The idea of superposition is that in linear systems and systems with op-amps are still linear devices. In linear systems, you can measure the impact of each supply independently. So in linear systems, you can look at the impact that each source has on any particular node independently, do that for every single source, and then add them together to get the overall answer. So it's a really handy feature. And what that means is, if we're trying to analyze Vn, we could, first of all, set this source to 0. What's a 0 volt voltage source? A 0 volt voltage source is a wire. So we could set that to 0 by replacing it with a wire. Now RL doesn't matter. RL shouldn't matter at all, but RL is shorted, so it's pretty obvious it doesn't matter. So the question is then, what's Vn? With this source set to 0, with that voltage source set to 0, 0 volt voltage source is a wire, what's Vn? Well, it's pretty obvious. We just have I in flowing through that resistor producing Vn. So Vn in this case is going to be I in times R. So now we're going to go and we'll just call that Vn1. That's our first measurement of Vn is given by that. Let's put that supply back. And let's now say, what if we set this other source to 0? Well, what's a 0 volt current? What's a 0 amp current supply? A current supply that produces 0 amps is just a break in the circuit. It's an open circuit. So we replace, with the way we set a current supply to 0 is we leave it open circuit. Well, now this is interesting. Now, what's Vn? Well, now Vn is, there can be no current flow through here, right? There can be no current flow because we have a break in the circuit here. So if there's no current flow, that means there's no voltage drop across this resistor. And if there's no voltage drop across this resistor, and this node is VO, then it means this node also has to be VO. So Vn2, analyzing Vn the second time, Vn with the current source set to 0 and the output supply left, Vn2 is simply going to be VO. Now we can find the overall Vn then by just adding these together. So Vn is I input times R plus VO. Okay, why does that matter? Because Vn, we know that V out equals A, which is the open loop gain for the op amp itself, times Vp minus Vn, correct? So Vp now is going to be 0. So V out equals A times negative A times Vn. And plugging in Vn, we have V out equals negative A times I1R plus V out. Okay, now we're almost there. We have an expression that relates our output and our input, but let's go back. What version of our equation do we need? Going back a slide. We need an equation that looks like this. And the key thing here is this input term has to be bare. So we can't have any coefficient in front of this input term here. So looking back, we have this pesky little r here. So what are we going to do? We'll factor out that r. So we'll not factor it out. Sort of, right? We'll distribute it, or I forget the terminology. It's embarrassing. What is it called? Factor? I mean, it's factored out. I don't know. These things happen. These things happen. The good thing is I already passed this class, and I already passed my math class, and I got a degree, and I got a PhD, and you can't take it away from me. So I don't have to remember what it's called. So pulling that R out of there, we'll just pull the R out. Yeah, V out equals negative A R times I input. But we just, we pulled an R out of this, and this didn't have an R, so it's got to be 1 over R times V out. Okay, looking good? Do we look like our equation back here? Almost, except the equation had a negative sign here. So instead of saying plus, we're going to say minus a negative. Okay, so we've now gotten our expression into XO equals some coefficient times x in minus blah times VO. And what's this? And what's this? So this is now my A epsilon, and this is now my B. And we have that here. So we have A epsilon is that, B is that. Now, all this work that we just did, this description of superposition, this is all kind of left out of the book. So I try to cover it here. Sometimes people just need to see it actually written out. They need to see the work done for it to actually click. So that's what we're doing now. We're just doing it. So what does it mean now? So now that we know A epsilon and B, now we're off to the races, right? Because now we know open loop gain, we know the feedback factor. That's all we need. Once we're relying on the op-amp model, that's all we need to do this. So what, for instance, what's the loop gain? The loop gain is always going to be AE times B. In this case, when we multiply these two things together, we get A. Now this is maybe a bad example, right? Now this is, one thing to note here is, it's not a bad example, it's a great example. The thing here is the open loop gain of this network is not the same as A. So A epsilon is not equal to A. It's not equal to the open loop gain of the op-amp. It's equal to negative A times R. So very important to remember, A epsilon is not necessarily the same as A. The forward gain is not necessarily the same as the open loop gain through the op-amp itself. Okay, and what else can we know about this? So what's our equation? What's our overall equation? So we buried the lead here a little bit. My slides don't have it. What's the overall gain of this system? So the gain of the big A gain of this system, which is going to be V out divided by I in. That is given to us, we know from our analysis last time, that's going to be 1 over B times 1 over 1 plus 1 over L. So that's going to be, I ran out of room on this slide. Start erasing stuff here. I'm making it worse. All right. So what's 1 over B? 1 over B is going to be negative R. So A equals negative R times, times 1 over 1 plus 1 over A. And again, we just, okay. So gain is equal to negative R. Where have we seen that before? Where does that look like? That looks like our inverting amplifier. So, and it turns out, and we'll see later, this is the topology for an inverting amplifier. With some tweaks. The inverting amplifier has some tweaks. Okay, now naming. This is the part I hate. I hate talking about this. When we talk about amplifier topologies, we've talked about the 4 standard types. Right? We have the voltage amplifier, the current amplifier, the transimpedance amplifier, the transresistance amplifier, right? You have current in, current out, current in, voltage out, voltage in, voltage out, voltage in, current out. And each of these topologies works a little bit different. So one of the concepts in amplifiers with feedback is, how do you sample the signal that's being fed back? And when you feed it back, how do you combine it with the input? And so one thing to note is, in this case, we were producing some V out here. And the V out that was produced here, it didn't matter what load resistance we had, right? We could have had as much load on here as we wanted, and V out would have stayed the same. And so what we're doing is, this amplifier is sampling this output voltage. And how do we sample output voltage? If we're measuring voltage with a multimeter, what do? We put the leads of the multimeter in parallel with the thing we're measuring. That's how we sample voltage. We sample voltage in parallel, which is also called shunt, right? So parallel, shunt is a term that's used to refer to parallel. So anytime we're using voltage as a feedback signal, we are measuring it in parallel, we are measuring it in shunt. So we would say this output is being sampled in shunt. But then what's happening here is we have some input current and we are producing whatever feedback current is necessary to cancel this out. Why do we have to provide feedback current that cancels this out? Because we can't have any current flowing into the amplifier. So basically the net current flowing into the amplifier has to be 0. So what this is doing is our amplifier is producing sufficient feedback current to cancel out the input current. But what's really happening, another way to think about that is essentially you have some feedback current flowing out here and some input current flowing in. And these are being combined to be equal to 0, or they're being forced to 0. So the combination of these is being forced to 0. These currents, though, are being combined in parallel. So currents combine in parallel, right? If you have two current supplies in parallel, what do? They add, right? So current supplies add in parallel. What do currents in series do? Currents in series break things. You can't have two different currents combined in series because currents can only combine in series if they're the same magnitude. So anytime we're comparing two currents, we are going to combine them in parallel, which is also called shunt. So when we are adding two currents together, we add them in parallel. When we are measuring voltage, we measure it in parallel. So this topology is called shunt-shunt because we measure voltage in parallel and we combine currents in parallel. This is really becomes a problem, right? Because essentially we're using the term shunt to refer to voltages and to currents in two different ways, right? We're talking about combining and measuring. We measure the output, we combine at the input. So it's a little strange though, but this is called the shunt-shunt topology. This is also called voltage shunt. So to make things even worse, the book that we use, the Franco, which is a good book, but you know it's dense. It's a dense book. It uses the shunt naming convention. So basically, it says the first term for shunt-shunt. The first shunt is referring to the fact that we are combining currents in shunt to the input of the amplifier. The second shunt is we are sampling the voltage in shunt for the amplifier. This is also sometimes called voltage shunt. Voltage shunt means we are taking the voltage output, so we are sampling the output voltage. So we're sampling the output voltage and we are combining signals in shunt at the input. So voltage, so you see my frustration here. I always try to come up with a good way to describe this, and I hope I've done okay. We'll talk about other topologies, but basically, if you see shunt-shunt, or the alternative to shunt, maybe I should use a better example. The alternative to shunt is series. So if you see series and shunt used in a name, those two words are referring to how the input is combined and how the output is sampled. If you see voltage and then shunt or series, or current and then shunt or series, that is the first word is referring to how the output is sampled to provide feedback. And the second word is referring to how those signals are combined at the input. Okay, so, and again, different books, different people are going to use these different terminologies to refer to these topologies. But I'll try to refer to them as both, so just so you know both. And I'll try to touch on this again because I feel like every time I try to explain this, I feel like I've made everything worse. So we'll just keep going at it, right? The way we learn is by repetition and failure. So there's plenty of repetition and failure in this class. So okay, now here's the other thing to make things even worse. It's usually pretty obvious how the output is being sampled. It's usually pretty obvious whether we're sampling the current at an output or the voltage at the output, but the input's not always so easy. The input can be sometimes very hard to determine. It's not as simple as just saying, is my input a voltage signal or a current signal? because a voltage signal or a current signal can be easily converted into the other by just using a resistor. The issue is, how are the signals combined at the input of the amplifier? And usually a quick check that I tend to like to do is I like to say, if I wiggle my input, if I increase or decrease my input, in the ideal case, do the terminals of the op amp change? Do the voltage of the terminals of the op amp change? If by wiggling the input, the voltage of the terminals op amp at the terminals of the op amp go up and down, that's usually a good sign that I'm actually combining things in series. And if I wiggle my input and the voltages at the op amp don't change, that usually means I'm combining things in shunt. So typically, if I wiggle my input, regardless of whether the input is a voltage or a current, if my inputs to the op amp if their voltages don't change, then very likely what's happening is somehow I'm converting that input to a current and then comparing two currents. So that's my quick check for me. The thing is, I don't see that written in any textbook. I don't see any textbook that uses that shorthand. That's just what I use. So I could be wrong. So be careful. This has not been vetted. This is so far it's worked for me, but it could be just one of those things where it's just worked for me because I haven't seen these weird special cases. But in general, my quick check is, if I wiggle the input and the voltages stay put, then doesn't mean they're zero, right? They could be 3, right? They could be, but if I wiggle the input and the voltages stay put, usually that tells me that I am combining things in shunt at the input. Okay. Okay, let's do another example. Let's just crank through examples. So again, this is an example you'll find in the book. I like to add a little extra detail. So I like to give a little bit more in-depth stepping through these problems, because the homework problems expect you to do a more detailed analysis. I figure I'll give you the details of the analysis. I'll sort of go back to basics, give you the details. Let's do it multiple times. Again, if you're getting tired of hearing my voice, speed me up. Set that thing to ×2 or ×1.5. And then I'll talk really quick, and I'll sound like a Micro Machines guy. If I talk like this and you just spit up the video, it's going to sound really weird. So, and I'm a little alone when I'm making these videos. I'm talking to you on the other side of time and space. So I get loopy. I swear I'm not on chemical substances. So it's just how I am when I'm alone in front of a computer. Okay, let's look at this circuit. So this circuit, we have an input voltage supply here, and we have an output voltage. Now, I'm going to do my quick check here. If I wiggle this input voltage, does the voltage of my terminals of the op amp increase and decrease? It does. Looking at this op amp, because my input is connected directly to the positive terminal, in the ideal case, if I increase this voltage, the positive terminal voltage increases and correspondingly the negative terminal voltage increase. So if I wiggle the input and it causes the terminals of the op amp's inputs to wiggle, then that tells me that this is a series combination, and we'll talk about it a little bit more. But so in fact, it is labeled series, and then the output is a voltage, and we're sampling that voltage. So we're sampling in shunt, we're sampling in parallel. We always measure voltages in parallel. Okay, so if we are analyzing the circuit, we know that V out is equal to A times this voltage differential. So basically we can say V out equals A times VP minus VN. And we know VP, right? VN is connected to VP. So we can just say that is VN. But now what's VN? For VN, that is VF, and we're going to have to do our equivalent circuit model. So looking at this circuit, to solve for VF, we find the equivalent circuit, which is going to be okay. And again, now there is this RL over here, but that RL is in parallel with that V out. So RL has resistors in parallel with the voltage supply have no impact on the rest of the circuit. So a lot of times we just don't show it there. It's not going to mathematically impact our model. So sometimes we just leave it out. It is there, obviously, it's still part of the circuit, but because it's a resistor in parallel with the voltage supply and we don't care necessarily what current's flowing through it, not right now at least, we can just leave it out. So what's VF? Looking at this circuit, we just have a simple voltage divider. So VF, in this case, based on the voltage divider formula, is going to be VO times R1 divided by R1 plus R2. So plug that in here, we get V out equals A times Vn minus R1 over R1 plus R2 VO. And the cool thing is this is already in our form. This is already in the form we need. So this is already in this XO equals A epsilon times X in minus B X out. So it's already in that form. So what's our A epsilon and what's our B? Well, this is pretty neat, right? Because now in this case, A epsilon equals A. So for this circuit, it is true that A epsilon is equal to A. After we warned so many times A epsilon is not A, sometimes it actually is. So in this case, A epsilon is A. And B is going to be R1 over R1 plus R2. Or it can be rewritten if you want to rewrite it. If you want to divide the numerator and denominator by R1, you can get it in the other form. And the loop gain is the product of these two. And the loop gain is this. So now what is the gain of this amplifier? Well, the gain of this amplifier we know from last time, it's 1 over B times 1 over 1 plus over L. So that's going to be 1 over B is going to be R1 plus R2 over R1 times 1 plus 1 over 1 plus 1 over L. Okay. So this is maybe where this version is even better, right? Because this version, let's replace this with the inverse of that. The inverse of that is 1 plus. Where have we seen that? Where have we seen a gain of 1 plus the ratio of resistors? Well, that's the non-inverting amplifier. And what does this circuit look like? It looks like a non-inverting amplifier. So basically, we got back to the non-inverting amplifier equation by going through the analysis as a feedback network. So we can always eventually get back to this. And you might say, why then? Why did we go through all of this? Because when we analyze this system as a feedback network, this is already given to us, right? I was able to pull this equation out of last lecture. I didn't need to resolve this. I didn't need to solve for, oh, what's the impact if alpha is 10 to the 4th instead of 10 to the 6th? I already know all that. All I had to do was find A epsilon and B, and now all of my equations for all of those non-ideal cases are already known. We established them last lecture. Now we can just plug in the values once we find them. So, okay, now this topology measured the output combined. So measured the output in shunt, combined in series. Now, what does this combined in series mean? Well, keep in mind we had the input was connected to one terminal of this amplifier. The feedback was connected to the other terminal of the amplifier. What do op amps do? They subtract the two differences. And subtraction is just a form of addition, right? So we're adding these two signals together. We're adding the negative of the signal. We're adding the negative of the negative to get that feedback. So this is, that is the series combination. That's why we call that series. We are adding things. We are adding two voltages. We are combining two voltages. Voltages always combine in series. If you have two voltage supplies in series, they are added together. What if you had voltage supplies in shunt? What if you had voltage supplies in parallel? Well, you can't do that. If you have voltage supplies in parallel, you're going to break something, right? Voltages are always combined in series. Okay. I always feel like I'm making things worse whenever I describe things. So hopefully, and the other name for this is voltage series. So again, you can always take the first word, make it the second word, and then just say, well, is my output a voltage or a current? A voltage series. Okay. Okay. Let's do series. So series, current series. So let's think about what that means. Just going by the name. Series means we are combining currents we're combining voltages at the input. We're adding voltages in series at the input. And we are sampling in series. Sampling, we sample voltages in parallel, we sample currents in series. What does that mean? Well, if you're ever measuring current in the lab, what do you have to do? You have to break the circuit. You have to break the circuit, insert the current meter in series with your circuit to measure current. That's what we're doing. We're measuring current here. So what does that mean? That means we are measuring, in this case, we have a load resistor. We have some current flowing through it. We are measuring the current flowing through that load resistor. Okay, let's see what that means. So let's analyze this circuit. So for this circuit, we know that we are sampling the current output, but the thing is, op-amps, the actual core op-amp is a voltage amplifier, right? We're adding these resistors around the op-amp to measure current, but the op-amp itself is measuring voltage. So the op-amp will still give us, the actual op-amp equation is still going to be V out equals some input differential times the gain times alpha, not alpha epsilon, just times alpha. But what we're gonna have to do is, we know this is sampling the current, so we're eventually going to have to massage this equation into I out versus V in. So if we just solve this for V out, V in, we're not going to get a full picture of what's going on here, because we're not actually, I mean, eventually we will get back to the same equations, but we're going to think this is doing something that it's not when we're doing this analysis. So just note that we've identified that we are sampling the current in this case. And so we eventually need to get the equation in the form of I out versus V in. So knowing that, let's jump in. So we have our equation for the op-amp is going to be V out equals A times VP minus VN. VP is fairly easy because VP is simply going to be VN. And then Vn is going to be what? So Vn is going to be, well, let's do our equivalent model here. Doing our equivalent model, we have so doing our equivalent model, we have so VF here, this voltage, and keep in mind this, sorry, we're kind of plucking this out here. VF, this voltage is sort of getting pulled out here to get sampled. Well, sort of get sampled. So we have VF equals, well, this is just a voltage divider, right? So this is just VF equals VO times R over R plus L. And we'll use that later, but we're not going to use that right now, because right now we have an easier way to write Vn. Vn here, which is VF, right? So I don't know why it's labeled VF here. But this voltage at the negative terminal can easily be written in the form of the output current. Right? It's simply going to be the output current times R, right? VF is this voltage across this resistor, which is the output current times R. And that's what we want. So we want, in this equation, we want to represent things in terms of the output current input voltage. We are sampling current and using that for the comparison. So let's take this equation, rewrite it. V out equals A times V in minus IOR. We have a problem here though, right? We have V in, that's good. We have I out, that's what we want, but we have this V out. So this is where we're going to pull from this equation here. So we are going to, oops, sorry. Yeah, this is where we're going to pull from this equation here, where we can say, oops, so VF equals V out times R over R plus R. But we also know that VF is IOR, right? So remassaging this equation, we get V out equals IO times R plus RL over R. So V out equals IO times R plus RL. Okay, the problem is this is not in the form we need it, right? We can't have this coefficient in front of here. So let's divide both sides of this equation by R plus RL. Boom. Okay, that's what we need. Okay. So now this might raise the question of sort of the, how did you know that how did we know in this circuit that we were sampling current? So right, essentially what's happening here is whatever current is flowing through our output also has to flow through this resistor R. So we are sampling that, we are using R to sample the current in series, right? You know, R is in series with RL. So we're using resistor R to sample this current in series. And then R is converting that current that we sampled into a voltage, which is what we're adding to VI. So this is the voltage, which is proportional to the current, which was sampled in series, which is now being combined with the V input. But the question is, how did I know that? Like this circuit, okay, you know, I can describe what's happening here that way, but what's a test? You know, like I said for the input, I said, if you wiggle the input signal and the terminals change and the terminal voltages wiggle also, typically that means you're series, you're combining in series, you're adding voltages, combining voltages. Well, is there a test for the output? There is a test that I use, and again, I don't pull this from any textbook, but the test that I use in my head is if I change the output load, resistance, does my voltage change? So if I change my output load resistance, if I wiggle my output load resistance, does my voltage change? In this case, it would. In this circuit, if you increased your output load resistance, the op-amp would have to provide a greater V out in order to maintain the same voltage at this terminal, right? It would have to provide a greater V out to keep the current the same, to produce the same voltage across that resistor R. So that's my personal test is if changing the output load resistance changes the voltage at the output of the op-amp, then you're probably sampling in series. You're probably measuring your current output. So that's my test. And that's if it's not obvious that you're measuring current output anyway. So that's my test. And again, if you know that you are sampling current, you need to use IO in your equation. And if you know you're combining voltages, you need to use it. So now here, what's my test for the input? My test for the input is if you wiggle your input voltages and the potential of the terminals wiggles, does that happen here? Yeah. If you wiggle VI, boy, I had made a mess of this slide. This whole lecture is a mess. I'm telling you right now, this lecture feels like a mess. This is a train wreck. Unfortunately, I think this is about the best train wreck I'm capable of. So I apologize, but this At least this is a detailed train wreck. The textbook is the train wreck is sort of hidden by just, here's the equation. We're going to hide the train wreck. So there's no hiding it. You're seeing how the sausage gets made today. So this is you're getting the full dose today, but it feels bad. I'm telling you, being on the teaching side of this feels pretty nightmarish, but hey, it's close to Halloween, or it's close to whatever holiday you're watching this video close to. So spooky, right? So we wiggle the inputs. If you wiggle this input, does the voltages of the terminal in the op amp wiggle? Yes, obviously. This input voltage is connected directly to the positive terminal. So if you increase the input voltage, the terminal's voltages are going to wiggle. So using that test, wiggle the input. Do the terminals wiggle? Yes. Wiggle the output load resistance. Does the voltage wiggle? Yes. This is a series circuit, which means we need to find output in terms of I/O and the input in terms of VN. So, okay, so hopefully that all made sense. Oh, so we got it. So now this term here is our A epsilon. That's how the book got that. It's like we found it too. And then this term here, maybe it should have been on this side, but this term is our B, which is our R. So what's in the loop gain is the product of the two. What's the overall gain, the big A for this? It's going to be 1 over B times 1 over 1 plus 1 over L. And that's going to be, let's forget about that for a little while. 1 over B in this case is simply going to be 1 over R. So the gain of this is going to be proportional to 1 over R. And that makes sense, right? So as R gets bigger, it takes less current to make the same voltage. So the gain, okay. Train wreck. All right, now Shunt-Series. This is the one that we're going to talk about. This is the last configuration we're going to talk about, and we are not going to go into a detailed analysis of it. There's a problem in the book. I think in the 4th edition of the book, it's like problem 1.53 has you derive this, but I went through it and I derived it, and the problem with the derivation for this is it's so I did have in my notes for this lecture the full derivation of this, but I don't think it helps anything. The problem is this turns into a very ugly equation, and it's an ugly equation that you need to rely on simplifying assumptions to get a clean solution to this. So if you look in the book, they have these sort of equal to equations. So this sort of equal to, they're making assumptions about alpha being big in order to find these sort of equations. If you don't do the sort of equations, you're going to have a big ugly circuit here that's going to have an alpha in it. So your gain term is going to be a function of alpha if you don't clean this up, and both of them become a lot more nightmarish. So they're doing these approximate solutions, but we can still talk about this circuit. Basically, you have an input current here, and if we don't want to just think about this, if we were analyzing this in the ideal case, we'd basically say, okay, this voltage is 0, there's no current flow, so whatever current flows in here also has to flow through here. But let's think about that in the case of a shunt combination. Let's think about this from the perspective of a shunt combination. Shunt combination, basically, one thing we can look at this is we have some output current here, and we can think of it as this output current is getting divided between these two resistors here. So the output current is essentially going into this current divider. And some of this output current is flowing through R1, and some of this output current is flowing through R2. And one way to think about it is we have this, whatever portion of this output current that flows through R2, and we have this input current flowing through I1, these have to sum to 0. So the sum of these, because there can be no current flowing into the negative terminal, the sum of this portion of the output current that's being divided across this current divider has to cancel out the input current. So basically, so they have to sum to 0. So they have to, which means ultimately that this output current is going to have to be negative of the orientation of the input current, and you can see that if if I clean up all the scribbles that I did, you can see that, right? That it has to be negative, the orientation of, we have this is going to be a negative, the overall gain of this system, the overall open loop gain of the system is going to be the inverse of 1 over b, which is going to be, it's going to be this negative term here. So thinking about this as adding currents together to where the sum is driven to 0, we can think of I input flowing through here and this portion of I output that gets divided across R2 also flowing into there and summing to 0. So that's maybe, if taking another stab at this, that's probably the best way to describe this, what's happening in this circuit. And you'll notice that description is very different from the way we analyze these in the traditional case. The traditional way we analyze these is we would just make the assumption that there's no current flow. So we would just make the assumption that you know, IN is essentially flowing all the way through here. But that's analyzing what's happened after the fact. What is really happening is we have feedback. We have feedback current being fed back, and it's being added to this input current, and they have to add to 0. The amplifier is driving this error to 0, or as close to 0 as it can get. So thinking about it, describing it 2 different ways is kind of important. It's important that the analysis that we go through traditionally with op amps is very different than what's actually happening at the system level, especially when we think about this as a feedback network. What's actually happening here is we are sampling an output, producing feedback, combining that feedback with an input, adding that feedback, taking the difference, right? That's functionally what's happening in this sort of a system. Okay, so now let's go through an example of so we went through the 4 standard topologies of these sorts of networks. Let's go to a common circuit that we haven't looked at yet. So this is, you can look at this, you can say, I know what this is. What is this? This is the inverting amplifier. This is an inverting amplifier circuit. But let's analyze the inverting amplifier. It's a simple circuit, so the math shouldn't be too hard. Let's analyze it though with a feedback approach. So the first thing is I might say with this circuit, voltage in, voltage out. What is this? This is obviously going to be a series shunt, right? Because, well, let's test, right? Let's do our test. So let's wiggle the input. If we wiggle the input, do the input terminals of the op amp change? No. This is the non-inverting amplifier. The positive terminal is grounded. Terminals stay at 0 volts, no matter what the input voltage is. The terminals stay at 0 volts. So that should cause us to go, okay, I wiggle my input, the input terminals of the op amp don't change, which means probably what's happening is I'm converting this input to a current, and I am actually doing an input combination in shunt. So by our wiggle the input test, this is actually a shunt input. And what about the output? Well, if I connect a load here, if I change this load, this output load, does my output voltage change? No. So we are sampling the voltage. So we are sampling the voltage. So let's go back to our shunt-shunt example. So this is shunt-shunt. So we had a current input, feedback resistor R. Okay, so refreshing our memories on what our shunt-shunt looks like here, let's analyze this other one. So one convenient thing to do is we don't actually have an input current here. Right? Our input is a voltage, but we can make an equivalent input current. We can take this and we can do a source transformation. If you remember source transformations from 111, if you don't remember source transformation, you can go through my EE 111 lecture series video series. You can look up also at the end, just like superposition, it's near the end of the chapter 4 lectures, you'll find source transformations. So we can transform this into a current source. So we could say we could transform this. So transforming this into this circuit gives us, well, I'm going to have to redraw it. My penmanship is very bad today. So we'll just redraw this as a current source. And then this current source is going to be, by the source transformations, Vn over R1. Okay. Okay, but we'll also just call this I input. So again, this is a shunt-shunt analysis. So we want our equation to be of the form In compared to, so In versus VO. So we want an equation of In and VO. Okay. We just have to know, we just have to remember that In equals Vn over R1. So we're going to come back to that later. Okay, so analyzing this, we always start with our op-amp equation. So we say V out equals alpha times Vp minus Vn. So Vp is just 0, so it's alpha times negative Vn. What's Vn here? Well, it's time to do our equivalent model here. Okay, looking at our equivalent model, we're trying to find this Vn is right here. How can we find this? You can choose whatever option you want to find Vn here. So let's do something different, actually. So we could do superposition. The book likes superposition. Superposition would be fairly easy, right? Because it would be one voltage divider. It would be one voltage divider and then the current flowing through two resistors in parallel. So it would be pretty easy. But let's make, at the risk of making an already disastrous lecture worse, let's use a totally different technique for finding this. So just to show that you can do it, let's use node voltage to find this. So node voltage to find Vn. So to find Vn, so writing the node voltage equation here, we have the sum of the currents equals 0. Again, if you don't remember, E111 chapter 4. So the current flowing this way is going to be negative In. The current flowing down is going to be Vn over R1. And the current flowing to the right is going to be Vn minus VO divided by R2. All that equals 0. Okay, cool. So now let's get this Vn out of here. So we have Vn times 1 over R1 plus 1 over R2. And that equals I1 plus V out over R2. Okay. Dividing both sides through by this. So dividing both sides through by this, we have times 1 over R1 plus 1 over R2 to the negative 1. Now you'll notice this equation, 1 over R1 plus 1 over R2 to the negative 1, what is that? That's R1 in parallel with R2. So I'm just, for shorthand, I'm just going to call this, oops. Call this R1 in parallel with R2. Cool. Okay. All right. So now plugging this in for Vn here. All right. Now we have V out equals A times negative R1 in parallel with R2. Let's just factor that out right now. In plus V out over R2. I hope my head doesn't cut that off. What a mess. Okay, we are done, right? Yeah. Are we done? Yeah. Okay. So we have, yeah. So this is our, for this circuit, this is our A epsilon is going to be negative A R1 in parallel with R2. And our B is going to be 1 over R2. Cool. But now here's the thing, right? Is you might say, okay, well, if B is 1 over R2, then the gain, the overall gain of this system is going to be 1 over B times 1 over 1 plus 1 over O, right? What's 1 over B? So the gain is equal to R2. What? That's not right, right? This is an inverting amplifier. The gain of an inverting amplifier is not R2. So you might say something's going wrong here, but remember, we had to solve for this gain here is V out over I in. So right, so we were finding the gain for the output voltage versus the input current. But in fact, we're talking about the input voltage here. So all we need to do is say the voltage gain of the system is going to be V out over I in times I in over V out. Oh, sorry, I in over V in. And we know I in over V in is, if we just, going back to this guy that we just left stranded up here. So rewriting this, I in over V in equals 1 over R1. So this is going to be R2 times 1 over R1. That's the standard form, right? So V out over V in for this circuit is going to be, the overall gain is going to be R2 over, oh, it's negative, isn't it? Yeah, I left the negative out. Yeah. Oh yeah, shoot, we did, no, sorry, I made a common mistake. We can't leave it positive, it's got to be negative the negative. So P is negative, right? Woo! Screaming at your computer board. Look at this slide. Look at what I did. What have I done? I've made everything terrible. Hopefully, man, if you can follow through this lecture, give yourself a pat on the back. You deserve, what were those things like after baseball practice where you like twist the tops off, like the Kool-Aid slammers or whatever? Like were they the Kool-Aid slammers. They probably don't serve those kids anymore because they're just sugar in a bottle. And I love those. You twist the top off and cut your lip on the plastic edge. Okay, you deserve a Kool-Aid. Treat yourself because you held on to the end. We are now done with this lecture. What are the take-home messages? I buried you in a lot of mess here. Hopefully you stuck with me. If you did, I appreciate it. What's the take-home message here? The take-home message is we can take any op-amp circuit now, any combination of resistors. We can analyze it as a feedback network. We can find an expression. We can identify what topology of feedback network it is by finding, are we sampling the output current or the output voltage? Are we sampling in series or shunt? Are we combining in series or shunt? And once we identify the topology, we can find the equation we need to represent. We need to represent, XO equals alpha epsilon times X in minus B times XO. Right? We need it. We can find that expression, the relationship between the input and output based on the topology. Find that expression. Find those coefficients. And then once we have those coefficients, once we have A epsilon, once we have B, we're off to the races. All those equations for gain error, gain desensitivity, all of that stuff we can use from last lecture just by plugging it in. All we need is those two parameters. We just need A epsilon and B, and we can unlock all of those equations that we used in the last lecture. So that's the value here. The homework has you go through some of these problems. It basically has you analyze an op-amp circuit, find these coefficients, use the techniques that I did here. I think the really important thing about this section of the book is that ability to deconstruct the op-amp circuit. So find the equivalent model of the circuit, solve it using superposition, or as we did just recently, solve it using node voltage. Whatever technique you want to use to solve that equivalent circuit, do it. Massage the equation into the right form, take those parameters, and then find your A epsilon and your B, and you are good to go. So thank you again for hanging on. Sorry it got messy, but that's how this stuff is. I appreciate it. Have a good day.